Hi, I'm Nancy Jordan from the University of Delaware, and I'm going to present today on a fraction sense intervention grounded in the science of learning. My collaborator is Nancy Dyson, also of the University of Delaware, and this work was supported by a grant from IES. So, in today's presentation, I'm going to provide motivation for our fractions intervention efficacy study. First, I'll outline the research questions and methods, and I'll spend most of the time describing our fraction sense intervention that we developed for the project. But I'll also present preliminary findings with student work. So, the math problem. Despite considerable investment in research and mathematical learning over the past decade, low-achieving students are losing ground. The most recent U.S. NAEP report card reveals that 8th graders performing below the 25th percentile in math scored significantly worse than did a similar cohort of lower performing students in previous years. So rather than focusing on detailed sets of standards, such as the Common Core, it has been proposed that more attention should be devoted to developing powerful teaching approaches in crucial components of mathematics proficiency. So why fractions? Fractions are foundational for learning rational numbers and algebra, making them a crucial component of mathematics education in the middle grades. And those who don't pursue a college education or higher level STEM vocations, people still need to understand fractions to succeed in occupations requiring measurement, such as construction, healthcare, and food service. But fractions are hard for many students. Numbers of the same magnitude can look quite different. For example, 3/4 and 9/12 are the same amount, but the numbers are very different. Sometimes when numbers get bigger, the fraction gets smaller. So 1/4 is bigger than 1/6 or 1/8, but 4 is smaller than 6 or 8. But then this isn't always the case, because 2/4 is smaller than 6/7. And another concept that's very hard for many students is that there are infinite numbers between two fractions. And this is just a cartoon showing how confusing fractions can be and why students often will choose the fraction with the larger numbers as being bigger. He says, I understand they all have the same value, but I have to tell you, the ones on the right feel like more bang for your buck. Our previous research in a longitudinal study did show that many students show little growth in fraction magnitude understanding between 4th and 6th grades. And you can see on this graph, on the vertical axis is accuracy, and on the horizontal axis is the grade. And the lower the score, the more accurate the students are. So you can see there is a class of students who start quite accurate on fraction magnitude tasks in 4th grade, and they continue to be very accurate through 6th grade. And then there's another group of children who start out inaccurate, but through the course of instruction, they develop a lot of understanding, and they are quite close to the achievement of the higher performing students. But then there is a class of students we're concerned about, and this was about 1/3 of our sample, where they start out inaccurate in 4th grade, and they continue to be very inaccurate throughout the intermediate grades when the bulk of fraction instruction is provided. So this was very concerning to us. Now, students are often confused by common teaching methods in class, such as the butterfly method, which emphasizes procedures rather than understanding. And students can get the correct answer using the butterfly fly method, but they often have no idea why they're getting the correct answer or why a mistake might not make sense. So in response to these issues, we developed a fraction sense intervention. Our goals were to develop an effective intervention to help struggling students make sense of fractions, to ground the intervention in evidence-informed practices related to how children learn, and to develop a usable intervention for classroom teachers or interventionists in multi-tiered intervention settings. So we developed this intervention over multiple iterations. And we first developed the intervention to be administered by researchers in small groups of children with lots of materials, and we did find that the intervention worked very well. But then we realized that that kind of approach wasn't all that practical, because often interventions in the middle grades, and this was an intervention targeted towards sixth graders, often in the middle school grades or intermediate grades, interventions are provided in larger groups. So we realized we needed to develop something that would be more practical for teachers. So we developed animated PowerPoint lessons that could give the same, provide the same kind of information as the intervention we developed in small groups, but would be easier to carry out with more children. Then we mentored sixth grade teachers to carry out the intervention and found that it was quite usable. And then we did a pilot test with sixth grade teachers using the animated PowerPoint lessons with classes of 12 to 16 children, which then led us to our larger efficacy study to assess the effectiveness of the FSI. So basically, our research questions were, what is the FSI's efficacy with very low performing sixth graders in authentic school settings? And can teachers implement the intervention faithfully, and do they find it usable? And to what extent do student level characteristics, for example, attention, vocabulary, English language status, and special education status, influence student outcomes? Our design was a multi-cohort randomized study with sixth graders who were very low in math, which was determined by the school test. Sometimes it was the iReady or a similar test, and they were the students who were having the most difficulty in school. The intervention was carried out by teachers with professional development from the research team. And overall, we have 24 half-hour PowerPoint lessons, which were taught by teachers. The reason the lessons are half-hour is that they fit into the intervention times that are available in the schools, although this can vary by school to school, but we couldn't go beyond that. And we have a pre-test, post-test design with measures of fraction knowledge. So the data collected so far. To date, we have 14 FSI and 10 control intervention classes. We're a little bit behind because of the pandemic, and we had some trouble getting into classes, but now we're moving along quite well. And our target total is 48 intervention classrooms, which would be 24 FSI and 24 intervention control groups. So our findings to date, we've found significant differences between FSI and intervention controlled children. The intervention controlled children were getting the typical intervention math that they receive in school, which is often administered on a computer. In terms of fraction concepts, we found moderate effect sizes, applied problems, moderate effect sizes, fraction arithmetic, small to moderate effect sizes, and measurement, very large effect sizes. And all results were statistically significant at the 0.05 level. So now I'm going to describe the intervention and its components and what the PowerPoint lessons look like. First, we emphasize fractions as numbers with magnitudes, and fraction equivalence and ordering, and fraction arithmetic. We did increase our emphasis in fraction arithmetic because we did find this was the hardest area to see gains because many children had such entrenched procedures that were hard to change. Our approach was we explicitly incorporated principles from the science of learning, and we anchored instruction in meaningful context centered on visual number lines and fraction bars. We use clear and consistent mathematical language throughout. For example, the numerator and the denominator as opposed to the top number and the bottom number. And we use familiar denominators to develop deep understanding and to reduce cognitive load. So really, we started with very clear instruction with halves, fours, thirds, sixths, and probably not much more than eighths. We also did emphasize fluency with multiplicative reasoning. So at the end of each lesson, we would have a game that it was maybe no more than a minute or so, where children did work on this within a time context. So our FSI lesson overview. The FSI lessons are set to a backdrop of an ongoing story about helping plan a color run race. This unifying theme provides a real-life context that helps engage student interest throughout the lessons. Now, it's important to remember that typical fraction instruction for students with math difficulties emphasizes part-whole understandings using area models or set models that you can see below. So often, using these models, students think of 3/4 as strictly 3 of 4 parts, and so therefore they look for the 3 or the 4 in the diagram. And sometimes, often children do very well in these activities without really understanding what 3/4 means. And so the part-whole understanding does lead to difficulty when the number of parts in the whole don't match the denominator. The following are examples of student errors when the number of parts in the whole is 8 and the denominator is 4. So here, if the child is asked to shade 3/4 of the boxes, they shade in 3, which is incorrect because they had attended to the numerator only. Here, with the 8 circles, they attended to the numerator only and shaded in 3 circles. And then here, when they are asked to shade 3/4 of the 8 circles, they attended to the numerator and the denominator as separate whole numbers. So these are common kinds of mistakes we see in children at the beginning of the intervention and also children who are struggling with fractions. So the FSI focuses on fractions as numbers, and the number line is the most helpful tool for thinking about fractions as numbers. On the number line, the whole is always the distance from 0 to 1. Both whole numbers and fractions have specific locations on the number line. So between 0 and 3, we have 0 halves, 1 half, 2 halves, 3 halves, and so forth. It's important to understand that the value or the magnitude of the fraction is the distance from 0 to the fraction, not just the location on the number line. Fractions as numbers, the number line model also transfers easily to linear measurement, which is often needed in everyday life. So in terms of our instructional approach, the FSI aims to make explicit mathematical connections. And to make these connections explicit and to make learning stick, The FSI uses validated learning strategies from cognitive science, including multiple representations, gesturing, concreteness fading, retrieval practice, and clear feedback. And I'll explain how these are incorporated with examples. So, multiple representations, a strategy for finding 1/2. Well, you separate the whole into 2 equal portions and take one of the 2 equal portions and make 1/2. You could do that with an area block or on the number line or with a set of objects. So a simple concept of 1/2 could be represented in multiple ways. And of course, the ruler, which shows 1/2. Another example, the number line can easily be seen in the multiple representations. You can make a race course with the number line, or the ruler is essentially a type of number line. Images can be brought to scale, such as 1 inch equals 1 mile. And the number lines can also be sized to match diffraction bars. The distance from 0 to 1 would match the length of the whole bar the length of the bar representing the whole. And fraction bars can then be placed on the number line to help students make connections between an area model and a linear model. So here's the whole with the fraction bars. 4/4 is the same as 1. And with the animations of the fraction bars, these are made very explicit. Also, linear properties of representations that look less like a number line can be made explicit because the measuring cup really is just a vertical number line. We also use pointing gestures on the animated slides to support students' ability to shift attention between 2 related sources of information. Pointing can be achieved on the animated slides through arrows, circling, and boxing, and other animations that connect or draw attention. This puts less demand on working memory and frees up resources for processing new information and accessing prior knowledge. I'll show you. Once a concept such as fraction magnitude has been introduced, gestures can be used to extend students' understanding of the concept. In this example, a red rectangle sweeps to capture a group of fourths whose numerators are larger than their denominators, making their magnitude greater than 1. A common misconception among students who are having trouble with fractions is that all fractions are smaller than 1. And here on the number line, they can see that there are infinite fractions that can be greater than 1. The red arrows indicate that there is an infinite number of fourths greater than 1. In this example, the teachers model multiplication as 3 groups of 3/4 in the multiplication problem 3 times 3/4. So we have the arrows for the 3 groups of 3/4, and then the fraction bars that are 3/4 of the 3 wholes up top can be brought down like this. And then a red box is used as a conceptual gesture to reinforce the concept that the product is everything that's in the model, which would be 9. So the answer is 9/4. So the red arrows are once again used to connect the fraction bar model with the number problem, both representations of the concepts of groups of and the product. Concrete fading is another technique that we use to teach fractions. And here's an example again for multiplication as groups of. Very concrete would be what I just showed you, that the teachers use the app slides to model students' exploration of multiplying a whole number times a fraction. In this example, the animations mirror the students making 3 groups of 3/4 with their fraction bars. Then the teachers use the app slides to model drawings students create to further explore multiplication of a whole number times a fraction by drawing 3 groups of 3/4, showing that the wholes need to be the same and the sizes need to be as equal as possible. And then abstract, these models then help students multiply a whole number times a fraction with an understanding of why the numerator is multiplied by 3, but not the denominator, because we end up with 9/4 or 3 groups of 3/4. Also with multiple representations, they can be used to help children add problems with unlike denominators. So here we have 1/4 and 1/2. With the fraction bars, we need to trade like this. And in the race course, we need to trade like this. There's 1/4, another fourth, another fourth. With the 2/4 makes a half, which comes up with the answer of 3/4. Another important element of our intervention is to provide a lot of practice, and practice that requires retrieval. And one type of practice that has been shown to be very effective for all students is to prevent problems that are interleaved. And this would be presenting the same problem with a variety of operations, and which is a type of interleaved practice. And this type of practice helps students focus on the operation for each problem and to notice the differences in approaches to solving each type of problem. Now, for example, 1/4 and 1/4 would be 2/4. 1/4 minus 1/4 is a 0. 1/4 times 1/4 is 1/16, where the answer actually gets smaller. And 1/4 divided by 1/4 is 1. So again, the students, by having these, once they've learned to work with these types of problems, by having them together, the student can really think about the problem and what's needed to solve it. Interleaved practice also presents various problems that are related to a particular concept, but not identical in problem type or strategy used to solve them. Here's an example of the way the problem can be presented. 1/4 plus 1/4 plus 1/4 makes 3/4. It's an iteration of unit fractions, which is the same as putting an X on where 3/4 is on the fraction bar, and how long the pencil is, 4 3/4. And here's the one with the X where 3/4 is on the number line above. And then, of course, 3/4 of the boxes when the numerator does not match, when the picture does not match the denominator. And then finally, we do really focus on feedback, and often it's immediate, sometimes just delayed. But in this example, students are presented with a multiplication problem and the following prompt. They're asked to write the problem and the correct answer on the whiteboard, and which they are holding, and hold it up when I say go. Now, it's a very simple problem that we've worked on, and the children need to engage very quickly. And after the students have written their answer, the correct answer appears on the slide, providing students with immediate feedback about the accuracy of their response. And most children enjoy this kind of activity because it's fun, and they get the answer, and it's not like having a bunch of problems on a page that they have to answer very quickly, but it's one problem at a time. And if they're having trouble, the teacher can determine how to help. The problems such as these focus on student attention on appropriate strategies and can be easily interleaved in a fast-paced game presented on the PowerPoint slides. So I didn't have I will stop with the game example, but now I wanted to just show you some examples of student work before and after the FSI intervention in our study thus far. Here we have some examples of arithmetic problems that were what a child did at pre-test and then what they did at post-test. And for the first problem here, you can see the student with 3/4 and 1/4. The student added across came up with the answer of 4/8 as their procedure at pretest. But they were able to answer the problem 3/4 and 1/4 in a simplified form at post-test because they can understand how 3/4 and 1/4 makes 1, possibly by visualizing. The same student used subtracting across as their procedure at pretest for the next problem, but since the denominator became 0, they dropped it altogether. It's a perfect example of a lack of sense-making that 3/4 minus 1/4 would equal 2. At post-test, the student was able to write the correct simplified result using their fraction knowledge. And with the problem 2 plus 3/8, another FSI student showed no application of fraction sense at pretest, but instead used an incorrect procedural approach by adding the whole number plus the numerator to get 5/8. And when the fraction knowledge is applied at post-test, the result was very simple for them to calculate. Here's a multiplication problem. At pretest, this FSI student misapplied the multiplication procedure and again arrived at a nonsensical answer. And at post-test, the student made a model to check their thinking and arrived at the correct answer of 2. Here we have some practical word problems. The first one was Josh brought 1/2 gallon of lemonade to the party and Anna brought 1/4 gallon of lemonade to the party. How many gallons of lemonade did they bring all together? At pretest, this FSI student solved both the story problem and the matching arithmetic problem in the same way. They added across. So 1/4 plus 1/2 is 2/6. But at post-test, the same student solved both the story problem and the matching arithmetic problem the correct way. They found a common denominator using fraction equivalency, which you can see down here, and then they added correctly. Now, here are some examples of student work with the ruler, and this was very interesting. At pretest, this FSI student, and this is pretty representative of what we saw across all of our children, had no understanding of how to use a ruler. And at post-test, I mean, you can see when they were asked to, they just, again, gave pretty nonsensical answers. But at post-test, this student, as you can see, was 100% accurate. And most students in the FSI group were highly accurate with measuring at post-test, but also interestingly, few students in the control group correctly measured the items at post-test, suggesting that in their regular math intervention with fractions, they're not getting much with rulers. And it's such, there's such simple ideas that are very important that seem to be overlooked in most interventions. So this was an interesting result. Then we also asked students to order fractions to get a conceptual understanding. And again, at pretest, when they had to order from 2 3/4 to 4, you can see the students putting in fairly nonsensical errors when they didn't understand at a certain point, and then they become much more accurate at post-test. And here is a similar problem where the child struggled at pretest but did really well on this type of conceptual problem at post-test. And then also we did have some word problems where children were allowed to use the number line that's printed below under the problem. So it says, the problem says the Spirit Club bought 2 yards of fabric. They used 3/8 of yards of the fabric to make a race banner. How many yards of fabric do they have left? Well, at pre-test, they just kind of gave a random guess, but you could see at post-test that they were looking at doing kind of imitating the gesture movement from 0 to 1, 0 to 2, and then backing up to give the correct answer to of 1 and 5/8, which we also see in the other problem as well. So, key takeaways from our project and what we've seen so far and moving forward. We've shown that even students who are struggling mightily with basic fractions after 3 years of instruction can learn to make sense of fractions with the 24 lesson intervention that is supplemental to their regular math instruction in school. However, continued intervention is needed to build understanding and to make learning stick. We are doing delayed post-test with the children to see whether these skills continue, the growth continues to show over time, but we're hopeful that a lot of the strategies that we've incorporated will really help children generalize the findings and have them stick down the road. Teachers so far have carried out the FSI with fidelity, and they find it very useful in a variety of intervention settings. We think the FSI may also be helpful for younger students who are first learning fractions and may be at risk, or even for all children as kind of a basic kind of level of instruction. And also older students with more severe difficulties would benefit from the FSI approach. And although this approach does show promise, more data are needed to document efficacy in authentic classroom settings. So I wanted to give special thanks to the teachers and children who are participating in this project, and we welcome your thoughts and questions. Thank you so much. So the first question is there an optimal number of pointing gestures per slide? I wonder about overstimulation. That's a really excellent comment. We try not to over gesture and to really use them only in places where we think emphasis is needed. But I couldn't tell you that we've looked at the optimal number, but it is something that we definitely have kept in mind as we develop the interventions. So, and also to keep the students interested. Do you have student work beyond what we see in their answers on the pre-test and post-test? Were there any interviews of the students about their work? At this point, no, but we would love to do that down the road. Right now, we're testing in larger groups. So, we have to get data on a lot of children, and but we are spending a lot of time analyzing their strategies, and we are doing some questionnaires relating to the students' motivation and what they thought about the intervention. Do you have information about what was being done in the interventions with the control group? Was it consistent across students? Yes, we don't have the information now, but we haven't analyzed the data yet, but we are collecting information we are recording all of the control group sessions as well, audio recording. And so we hope to be able to see what the intervention teachers are doing, if they're applying some similar strategies, but they're not consistent across students because we're working in the real world. And so we kind of need to go with whatever the particular school is doing. Okay. How do the students receive this instruction? Do they demonstrate interest? They received it in groups of 10 to 15, I think. And they did seem to show a lot of interest. They really liked the slides and they liked the activities that went with them. And we saw, and I think the students also were feeling successful with the activities. Do you know if the students' regular textbooks programs relied on the conceptual principles that were included in the FSI? I don't know that information. In that, again, we are looking at what the control teachers are doing to see if there's evidence of those principles being used in that session, but we don't know about the textbooks, but that's a good point. Okay. Hey, Renee. Can I speak more about the entrenched procedures? I guess some of the earlier questions aren't showing. Should see. The entrenched procedures would be things, again, like the butterfly method that I mentioned, that it is a pretty good procedure for helping the student get the correct answer, but it is often not based on understanding. And we see that too with children learn to do certain things when they add and subtract fractions, but when they make calculation mistakes, the answers don't make sense. And so they're really, it's showing, like we have had some children that will go 1/2 plus 1/2 is 2/4, which just doesn't make any sense, but they've just kind of, they've started, they have a whole number bias, so they add across, and it's a hard thing to break. We had some children who were adding across even in 6th grade and subtracting across. Common denominators, which are the most simple arithmetic problems involving fractions. Okay, well, thank you so much. We're just about out of time. And I wanted to say, if any of you are interested in participating in using our slides and seeing how they work in your schools and classes, feel free to contact me. We hope they will be more available in the future. We have, since I did this video, we have gotten more results and they've been very promising. So I thank you for listening, and I hope to update you on results in future conferences.